All right, friends, 3 o'clock. Welcome back to your favorite class. Yes, dynamics. Yes. Speaking of favorite classes, you guys are probably signing up for classes right now. I'm teaching 2 classes in the fall that many of you can probably get into. All right, so if you've already taken the Mechanics of Materials sequence, which is 2004 and 3005, then you should sign up for Composites, which is ME2003, and that's what I teach, usually for seniors. So sign up for Composites. Rawr, it's exciting. All right, if you have not yet taken the mechanics sequence fully, then I'm teaching Mechanics of Materials 2, also in the fall term. So I have a Tuesday lab section and a Thursday lab section. It meets Monday, Wednesday, Friday, I think at 10 o'clock for the lecture. So if you want to take 3005 with me, then sign up for that. Rawr! If you don't like me, then don't sign up for it. Sign up with someone else. If you think my comedic hilariousness is stupid and you don't like my memes, then fine, don't come to my class. Take it with somebody else. All right. Announcements for the class. Your simulation number 3, which is on linkages, which you'll be doing in MATLAB, is going to be due next Friday. So that's the only announcement that we have. Today's going to be kind of a shorter lecture. I debated whether or not to start in on new material, which is the gears, but we're kind of ahead. So I figure I'll just finish out or round out the analysis on linkage by talking about the acceleration analysis, and then kind of call it for today. So maybe only 20 minutes or so on lecture today, and then I'll kind of get you out. All right. So is there any ado in the chat? There is no ado. No one is a Twitter. So let us get back to reality. Oops, there goes gravity. How'd you guys like my meme today? When you do the math problem completely wrong, but still manage to get the right answer. Oh yeah. Bugs Bunny. Did you guys watch Bugs when you were little? I watched a lot of Looney Tunes when I was little. It's kind of the big thing when I was little. That and like I watched Cat Dog, which was also kind of weird. Strange thing on Nickelodeon back in the day. All right. So, no more ado. Let us undo some dynamics. So I'm going to kind of go through the whole procedure and process really quickly again, just so we're all on the same page. And I'll make some analogies about what we've done so far to sort of round out what is the acceleration analysis without actually fully going through all the derivations associated with acceleration, because it's just a lot of algebra. We don't need to really do that. All right, so let's talk about linkages. And remember that generally our linkages, we're looking something like this. And we called this here a 4-bar linkage. Nope, that's our model. This is what we want here. That guy. Here, this is a 4-bar linkage. Yes, there's only 3 links. I know. All right, and so we had a model for this. And that model was what you've come to know and love at this point, which is this particular model here where all of the vectors don't make any sense. Yeah, I said it. Right? And what we're assuming about this guy is that we know some information beforehand about what's happening. Specifically, we're going to say that this particular link in our generic 4-bar linkage here is the driving link. So we're going to assume that we have some additional information about that particular link that we don't have about the other links. And usually that's the case, because usually you have some link in a linkage that is being driven by a motor. And so if you're driving with a motor, usually you have an encoder on that motor that can tell you where the position is and so on and so forth. That's the way that electrical engineers and mechanical engineers work in harmony to create these mechanical systems. Okay, so we're going to assume we know link lengths, which are little a through little d. All right, we know link angles. Let's just say we know the driving link angle, because we don't know all the angles yet. Which we denote with theta 2. And we're also going to assume that we know the angular components of this driving link. So the driving link angular velocity, which is omega 2, and we also know the angular acceleration. And we haven't talked about angular acceleration quite yet, but if we're driving this link, we would assume that we also know the angular acceleration, which we're at this point introducing as alpha 2, or as some of you students say, fish 2. Right? So these are the things that we have and that we know about this particular system. With these pieces of information, we went through a position analysis first. And our position analysis really started with what is the vector loop equation, which now you should know is something like R2 plus R3 minus R4 minus R1 is equal to 0. And so that just comes from our definition of these various position vectors that we're using to identify where these links are in space. So that was in your general vector notation, but if we want complex notation, we saw that this was something like A e to the j theta 2 plus B e j to the theta 3 minus C e j to the theta 4 minus D equals 0. This is our general expression that we came up with after using our complex notation and plugging into our vector loop equation. And generally what we saw here is, recall that this guy here is actually two equations. Kind of jumping around a little bit, stupid writing pad. This is actually two equations. One in the real space and one in the imaginary space, or one in I and j, or one in x and y, or however you want to think about it. And we have two unknowns, which namely is theta 3 and theta 4. So two equations, two unknowns. We solve this guy. For theta 3 and theta 4. Yes? And what we saw, because of kind of the craziness of the algebra associated with this equation, was that you actually get two answers for each of theta 3 and theta 4, corresponding to a open and a crossed configuration. So you had something like theta 3 configuration 1, configuration 2 is 2 times tangent inverse of a bunch of stuff, and theta 4, 1, and 2 is 2 times tangent inverse of a bunch of stuff. Hoo-ha, 2 times Thursday. Oh, boo. All right. So that's what we generally found from that analysis. All right, so now we have full positional information about our linkage. All right. All right. So now we've got our full position scoped out, and we kind of talked about how to calculate those angles theta 3 and theta 4, and we saw lots of algebra, and it was annoying, and then you decided, I'm sick of this, I want to go to MATLAB, and that's good, because that's where you should be going. Don't go to Excel, I'll be upset. Excel, terrible. It's terrible, just terrible. All right. So after our position analysis, we did velocity analysis. And at this stage, we know the link lengths A through D. We know omega 2, and we know our positions theta 2, theta 3, 1, 2, and theta 4, 1, 2. All right, these are all the things that we have at this particular time after we have done our position analysis. So once we have all these things, we then again go to our vector loop equation, which is R2 plus R3 minus R4 minus R1 equal to 0. And we took the time derivative. Right. So after taking the time derivative in complex notation, we saw an equation that looked like J A e to the j theta 2 times omega 2 plus J B e to the j theta 3 times omega 3 minus J C e to the j theta 4 times omega 4 equal to 0. So that's what happens after we took the derivative of our vector loop equation. Again, this guy, hopefully you're recognizing the pattern here. There is a pattern emerging. I hope you're catching it. Is that this guy, we have two equations, one in the real space, one in the imaginary space, or one in I and j, one in x and y, however you want to think about it. And now we have two unknowns, which are omega 3 and omega 4, here and here. Everything else in this equation or about this equation is known. All right. hopefully you're getting the pattern. We're going to use this pattern once we go to the acceleration analysis. So stay with me. So after solving this, you end up with various angular velocities that depend on the angles of theta that you use. So we will, again, just like in the position analysis, have two different configurations, an open and a cross configuration, giving us two different angular velocities for link number 3 and link number 4. So we have something like omega 3, 1, and 2 is equal to A omega 2 on B times sine of stuff over sine of stuff. So that's your angular velocity of link number 3. In open and cross configuration, and you have a similar looking equation for the angular velocity of link number 4, which is something like A omega 2 on C times sine of stuff over sine of stuff. All right, so again, we have angular velocities for the open and cross configurations. All right. Once we have the angular velocities, we can look at the linear velocities of the pins. And I will jog your memory here, and that the velocity of point A is something like J A omega 2 e to the j theta 2, right? Or if we write in our sort of complex notation, where we've kind of like distributed this first j that's inside of there to the rest of the piece, you're going to end up with the velocity of point A is something like A, oh, sorry, I lost my pen there, A omega 2 times negative sine theta 2 plus j cosine theta 2. All right, this is your velocity of point A. The velocity of B relative to A will sort of be given with information of sort of this link number 3, which is the second link in the chain, which uses the variable little b, but it's link number 3. Right. B omega 3. Don't forget your omega 3s. Very helpful. Negative sine theta 3 plus j cosine theta 3, where again it could be theta 3 1 or 2. So you're going to understand that you have these relative velocities for both the open and the cross configuration. So could have something like omega 3 1 comma 2, theta 3 1 comma 2, theta 3 1 comma 2 here. If you want the relative velocity of B relative to A for both the open and cross configurations, you can sort of denote it as such, but hopefully we kind of understand that. And the velocity of B, I guess if you want to say again with open and cross configurations possible, it's going to use link length C, omega 4, and here negative sine theta 4, 1, 2, plus j cosine theta 4, 1, comma 2. All right. And again, making sure that you're using all information about the open configuration to calculate the velocity of point B in the open configuration, and all the information about the closed configuration if you want to calculate VB for the closed configuration. All right, hopefully that's kind of well understood. So this is the pattern. We have the vector loop equation. We look at the real and imaginary components of that vector loop equation, and then some information falls out. All right, we're going to use this same pattern when we finally now go to the acceleration analysis. Okay. So in the acceleration analysis, we again start with the vector loop equation. But now instead of taking the first derivative with respect to time, we'll take the second derivative with respect to time. D squared dt squared of vector loop equation to get accelerations. All right, ready? Okay, let's go. So we need d squared dt squared of a e to the j theta 2 plus b e to the j theta 3 minus c e to the j theta 4 minus d equal to 0. We need the second derivative of that guy. All right. Well, what's going to pop out? I'm going to just cut to the chase here. And that you understand when we do the second derivative, there's going to be a real and an imaginary component to whatever equation results. You will understand that. The only two unknowns that we will have with those two equations that exist will be the angular acceleration of length 3 and the angular acceleration of length 4. So let's make that clear. Out of this, you'll have two equations, one in the real space, one in the imaginary space, or one in the ij, one in the x, one in the y, however you want to think about it. One in the real space, one in the imaginary space, and two unknowns, which will be alpha 3 and alpha 4. And since we have open and cross configurations, we could have angular accelerations in those open and cross configurations. So here we'll again denote the 1 and the 2 for the open and cross configurations. We could do all that algebra. It's not a good use of time. All right, I could sit here for 15 minutes and do all the algebra associated with this particular derivative, but it's long and it's annoying and not really fruitful. All right, what I'll do is I'll just cut to the chase and give you the equations for alpha 4 and alpha 3. You've already seen enough algebra associated with this complex vector notation. Hopefully you're comfortable with it. If not, what have you been doing the last 3 days? Okay. So I'll cut to chase. And we'll write that alpha 3 configuration 1 configuration 2 is going to be equal to, we're going to use some constants here, and these constants are different than constants that you previously saw. So just stick with me while I write this, and then I'll explain. So this is capital C, capital D, minus capital A, capital F, all over capital A, capital E, minus capital B, capital D. All right, here's your equation for alpha 3, 1, and 2. Similarly, alpha 4, open and cross configurations, going to depend on these constants. It's going to look very similar here. Capital C, capital E, minus capital B, capital F, all over capital A, capital E, minus capital B, capital D. All right. So here we are with alpha 4. All right. And this particular setup, we have these capital A through capital F, and this is different than the capital A through capital F that you saw when you calculated theta 3 and theta 4. So A through F here, different than A through F used in calc of theta 3 and theta 4. Okay, so remember theta 3 and theta 4 did something like the opposite of capital B plus or minus the square root of capital B squared minus 4 capital A capital C, yada, yada, yada. Okay, so note that here capital A through capital F for calculating alpha is different. All right, here we have the following for capital A through capital F. So here, capital A, and it's going to be different whether you're in open or cross configuration. So you can denote that with something like 1 and 2 is going to be little c times sine of theta 4, 1 or 2. Our capital B is going to be little b times sine of theta 3, 1 or 2. And again, capital C, this is a little bit difficult to like draw capital C because you've got a capital C here and you've got lowercase c kind of floating around. So make sure you know which is which. It's kind of hard to tell, but it's very clear in the notes if you want to look at the notes instead. Here, this one's a little bit crazy. This is little a times alpha 2, which remember we know alpha 2 because it's of the driving link. Sine theta 2 plus a omega 2 squared times cosine theta 2. This is going to be here plus b omega 3 either 1 or 2 squared times cosine theta 3,
1 or 2, and then here minus c omega 4, either 1 or 2 squared, times cosine theta 4, either 1 or 2. All right, sorry to kind of squeeze that in there. But this is capital C equal to all that stuff on the right hand, where this here is a little c. It's perfectly clear in the notes. If you want to take a look at the notes, it might be a little bit easier. All right. Continuing on, capital D here, again, could be either for open or cross configuration, is little c times cosine of theta 4, 1 or 2. And then capital E here, state 1 or 2, is b times cosine theta 3, 1, 2. And then finally our capital F, which looks a lot like what capital C is going to be a times alpha 2 times cosine theta 2 plus a omega 2 squared, sine theta 2 plus b omega 2, or should be omega 2, should be omega 3, comma 2 squared times sine of theta 3, 2. And then finally, for this last link contribution, negative c omega 4, 1 or 2 squared times sine theta 4, or 2. All right, so there are the capital variables that feed into the equations for your angular accelerations. All right, I'll give you a second here if you're still kind of working through this. My handwriting not the best. It's probably legible, but better if you maybe use the notes as a reference. Okay, it's part of the reason I post the notes is because I realize my handwriting is a little bit suspicious. Yes, little bit suspicious. All right, now that you have your angular accelerations, you can then plug those back into the linear acceleration equations to determine what the linear accelerations of the pins are. So now, accelerations of pins are the following. The acceleration of the pin at A is going to be a combination of the tangential acceleration and the centripetal acceleration. So for point A, it's going to look like something like A alpha 2 or A fish 2, if you like the fish notation, negative sine theta 2 plus J cosine theta 2. That's like your tangential contribution of the acceleration. And then here now we're going to subtract out the centripetal portion of the acceleration, which is A omega 2 squared times cosine theta 2 plus J sine theta 2. All right, and this is your linear acceleration of pin A. Where again, this is like the tangential contribution. Which comes from something like alpha cross R, if you want to think way back to your kinematics. And then this guy here comes from the centripetal acceleration component, which is coming from like omega cross R. All right, so you can sort of see that here. Omega cross omega is going to give us like an omega squared, which we see popping out here. R, the magnitude of this first link's length is A, and then the directionality associated is here embedded in the cosine theta plus J sine theta terms. All right, so there you go. It's all coming together all the way back to what you learned in week number 1. But now just in a different notation. It's complex vector notation. But don't be scared of it. It's not that complex. They should call it easy vector notation. Because it's so easy. Even a caveman could do it.
Similar looking equations for the acceleration of b relative to a. This is going to be information related to like that second link in the chain, which uses the link length of b, or the vector 3. God damn, it really makes me annoyed. But okay, so at b, alpha 3. You understand that this could be a 1 or a 2. I'm not going to write them just because I'm going to run out of space if I do that. So b alpha 3 could have open and cross configurations, negative sign. Theta 3 could be a 1 or 2, plus j cosine theta 3 subscript 1 or 2, minus the centripetal contribution, which is b omega 3 could be 1 or 2 squared, times cosine theta 3 could be 1 or 2, plus j sine theta 3 could be 1 or 2. So this is your linear acceleration of b relative to a. And then finally, the acceleration of point b. It's going to look at the third link in the chain, which uses the link length c, and the angular acceleration that you calculate from above is alpha 4. Negative sine theta 4 could be a 1 or 2, plus j cosine theta 4 minus c omega 4 squared. Don't forget your omega 4s. Good for your health. Cosine theta 4 plus j sine theta 4. All right, there you go. Thus concludes the linkage portion of the course. Yay! Except for one thing. You still got to do your simulation. Boo! No, just kidding. It's kind of fun. In a weird way. Just like my personality. Kind of fun in a weird way. All right, so that concludes linkage analysis. What I will tell you is that we have only done a thorough dive on what is the 4-bar linkage. All right, there are other linkages that exist. There's the 5-bar linkage. Imagine that. There's the 6-bar linkage. And wait for it, the 7-bar linkage. Okay, so on and so on and so on. You could have all these crazy like linkage situations and setups. And they get more and more complicated the more like links that you put into it. But the general process remains the same. Come up with a vector loop equation for that particular linkage and start taking derivatives to get the velocity and acceleration, right? The methodology is there. It's a little bit easier to handle in complex notation because derivatives of things like a e to the j theta is easy, because when you have an exponential derivative, easy to do. So it makes this analysis a little bit easier when you're going to more complicated systems. So they have like more links in a chain. You could also have like a slider situation. So if you remember back to our sort of piston driving the engine situation where you had that piston kind of moving around inside the engine, that's like a crank slider example. So that's another various type of linkage, but that just changes the vector loop equation slightly, and away you go. So what we've seen here is just sort of like a general analysis method, introduction to complex vector notation, and how we might handle it to do analysis of these complicated linkages. So hope you learned something. That'll be it for today. I'll start in on the new material tomorrow, which is on gears, and give you a break for the rest of the time. So with this 20 minutes that you have for free, I suggest that you start on your simulation for linkages while it's still in your head. All right, do it. That's it for today. See you guys later.